Hey everyone, welcome back. In the last video we already got to know several sorting algorithms like selection sort, insertion sort, bubble sort, merge sort and quicksort. And today I want to show you some implementation of these algorithms in Java. The core idea is to repeatedly compare adjacent elements and swap them if they're in the wrong order. So it would be good if you know a bit about Java, and hopefully by the end you understand how each one works and when to use which. So it's called bubble sort because with each pass, the largest unsorted element bubbles up to its correct position at the end of the array. So let's get right into it. First up we have bubble sort. It's one of the simplest sorting algorithms out there, but it's not very efficient. We start by initializing a variable n to represent the length of the array and a boolean flag called swap. This flag helps us to track whether any swaps occurred during a pass. So this is a key optimization to improve performance in the best case scenario. Then we have the outer loop, which runs through the array n-1 times. On each pass we assume the array might be unsorted and set swap to false. Then in the inner loop we iterate only up to n-i-1, because with each pass the largest element settles at the end, shrinking the unsorted portion by 1. Inside the inner loop we check if the current element is greater than the next one. If it is, we swap them and mark swapped as true. So after one full pass, if no swaps were made, the list is sorted and we break out of the loop early. Thanks to this optimization, bubble sort achieves a best case time complexity of bigger of n when the array is already sorted. However, in the average and worst case it still runs in bigger of n square, making it inefficient for large datasets. Next up is selection sort, another simple but inefficient algorithm. The idea is to repeatedly find the smallest element in the unsorted part of the array and move it to the beginning. So with each iteration the sorted portion of the array grows from the left side. We loop through the array and for each position I we assume it contains the smallest element. Then with a nested loop we search the remaining unsorted portion to find the actual minimum. If we find a smaller element we update our min index. So after the inner loop completes, we can swap the smallest element found with the element at position I. This continues until the entire array is sorted. Unlike bubble sort, selection sort performs fewer swaps, at most n-1. However, it still performs bigger of n square comparisons in all cases, regardless of how sorted the input already is. So because of that, selection sort isn't suitable for large datasets, but it can be useful in cases where memory writes are expensive and we want to minimize the number of swaps. Now let's look at insertion sort. This algorithm mimics the way we sort playing cards in our hand. Starting from the second element, we compare it to the items before it and insert it into the correct position in the sorted part of the array. We consider the first element as sorted, which is why we start by the index 1. For each index I, we take the current element as the key. And then with a while loop we compare the element backwards with the sorted section to the left. So as long j is greater than 0 and the key is smaller than the elements on the left, we shift those elements one position to the right. and go one element to the left with j-1. And then when we find the right spot, we can insert the key. The best case time complexity is bigger of n if the array is already sorted, and the worst case is bigger of n square, which happens when the array is sorted in reverse. It's also stable and runs in place, making it a solid choice for incremental sorting, or when sorting small datasets efficiently is more important than skippability. Next, let's move into more efficient territory with merge sort. The main idea is to break the array into halves, recursively sort each half, and then merge the sorted halves back together. Now for merge sort we need more parameters than the array itself. Now we get the array itself, an integer left and an integer right. Left represents the leftmost number and right represents the rightmost number. So first we calculate the middle element of our list and call the method recursively for the list on the left and on the right. We do this until each sublist contains only one element. Then we call a merge method to merge these two lists. The merge process takes two sorted subarrays and combines them into one sorted array. In this merge method, first we calculate the sizes of the two subarrays we want to merge, and then create temporary arrays L and R to hold the values from the left and right halves by copying the data from the original array into these temporary arrays. Then we initialize our variables I, j and k. I and j are pointers for the left and right subarrays and k is the position in the original array. And then with a while loop we compare the elements from both halves and place the smaller one into the original array. And after that we copy the remaining elements because one side might still have values left, to ensure that all elements are merged back correctly in sorted order. Merge sort has a consistent time complexity of bigger of n log n in all cases. This makes it a reliable algorithm for large datasets. The only trade-off is space. It requires bigger of n extra memory to store temporary subarrays during merging. Merge sort is also stable and it's commonly used in situations where stability matters or when working with large files or linked lists. Finally, let's look at quicksort, which is one of the fastest sorting algorithms in practice. Like merge sort, it uses the divide and conquer strategy, but it still works differently from merge sort. Instead of merging sorted halves, it partitions the array around a pivot element. Quicksort also gets more than one parameter. It gets the array itself, an integer low and an integer high. Again, low represents the leftmost number and high represents the rightmost number. The first thing we do is we check if the subarray has more than one element. If so, we call the partition method to divide the array around the pivot element. This function returns the final position of the pivot, and then we recursively apply quicksort to the left and right subarrays. In the partition method, we select our pivot element as the last element. The variable I keeps track of the position where the next smaller element than the pivot should go. We loop through the array from low to high -1. And for every element smaller than the pivot, we increment I and swap the current element with the element on the index I. So this moves all smaller elements to the left side of the array. Then after the loop, we place the pivot in its correct sorted position by swapping it with array of I plus 1. Now everything to the left of the pivot is smaller and everything to the right is greater or equal. And finally we return the pivot's final index so the recursive calls can continue sorting the subarrays. Quicksort's average and best case time complexity is bigger of n log n, but its worst case is bigger of n square, which can occur if the pivot divides the array very unevenly, like for example when the array is already sorted. However, with good pivot selection strategies like randomization, this is rare in practice. Even though it's not stable, it's in place and very fast, which is why it's widely used in real-world systems, including many standard library implementations. Also, I've made a small method, printArray, to print our array after we executed the sorting algorithm. Now we can head into our main function where we can call all sorting algorithms on an array. And we see that the resulting arrays are all sorted now. And there we have it, 5 fundamental sorting algorithms, each with their own strengths, weaknesses and use cases. Thanks for watching, and if you found this helpful, make sure to like, share and subscribe for more videos on data structures and algorithms, and we'll see us next time.